science. Here we are, back again, ladies and gentlemen, and this week we are going to be talking about something we can see and something we can't see. Yes, this is a very unusual topic this week. We really can't live without it in one form or another. Much of it is invisible to us, although some of it is visible to us. But we are exposed to this and bombarded by this every day of our lives. What in the world am I talking about? I am talking about electromagnetic waves. EMW for short. Electromagnetic waves. We had a little bit of an introduction yesterday to electromagnetic waves, and today and tomorrow we're going to further explore what these things are and write some things down in our notes. So let's get started here right away. Hopefully we'll have time at the end to do some activities with electromagnetic waves. The lights just went out. Wow. That's not what I wanted to do. Electromagnetic waves. I introduced you yesterday to electromagnetic waves and showed you a similar chart as this as to the distribution of electromagnetic waves and how these EMWs are made up of a lot of different things. Probably the most familiar combination of waves, electromagnetic waves to human beings, are those found in the visible light spectrum we see with our eyes every day. Every morning when you open your eyes, you see things. And the reason for that is because your eyeballs have structures on the retina in the back of your eyeball that sends signals to our brain. In fact, the back part of our brain, the visual cortex, and our brain interprets those signals as light. We see because of light. And light, visible light, is only one small portion of the electromagnetic spectrum. You may get burned in the summer from sunlight. You're actually getting burned by ultraviolet or UV light rays. You may have a bone broken, and your doctor may take a picture of it using X-rays. Both are parts of the electromagnetic spectrum. You may get warmed after a shower, perhaps, with a heat lamp in the bathroom. Those are infrared rays. Other rays include microwaves in your kitchen, radio waves, maybe in your living room with a radio. All of these different waves are part of the electromagnetic spectrum. Now, before we unpack them individually, what I'd like to do is just talk about waves in general. I want us to get a conceptual understand the big idea of what waves are and how these waves actually differ from other waves we might be more familiar with. So what is a wave? In its simplest form, a wave can be defined as a traveling disturbance that carries energy from place to place. Now, in this picture of water, we can see that something evidently has dropped into the middle of this water. We can see that because of, well, the evidence of it in the form of waves. We can see waves, water waves, working their way out from the center. So we can deduce that there must have been some energy source in the middle. Maybe a little pebble fell into the water or something like that. Whatever it may have been, we can see the traveling disturbance in the form of waves traveling through the medium of water. We can do the same thing if I were to make a sound. Let's get quiet for a moment. Did you hear that sound? You, the human ear, is able to detect sounds because of a source of energy, namely, it could have been my vocal cords when I scream out, causing a disturbance in the air molecules that go from my mouth to your ears. That is another example of a wave. But the waves we're going to be talking about here this week differ from water waves and sound waves. There are some similarities, but there are also some differences. So let's unpack that a little bit more as we talk about waves in the form of diagrams here that you will be copying into your book. So I've already mentioned that a wave is a traveling disturbance that carries energy from place to place. So let's illustrate in our books a source of energy, whatever that might be. Maybe it's a pebble in a pond. Maybe it's the air going over my vocal cords. Or maybe it's turning on a flashlight or a star igniting for the first time. Whatever it might be, there is some source of energy. And that energy is traveling or moving through something or nothing from one place to another. Now, water waves and sound waves, they require something to travel through. Water waves require water to move through. Sound waves require air to move through. But electromagnetic waves can travel through the vacuum of space. In other words, electromagnetic waves can travel through nothing. That's pretty cool. Through the absence of material in space. So, but that's a little bit difficult to understand. So, we're going to begin our exploration here by thinking of water waves. We probably can visualize water waves a lot better than electromagnetic waves. So we'll talk about the similarities here before we get into the differences. If you look at this beautiful picture here of a seashore, you can see that there is energy moving through the water. And we see that in the form of these waves crashing onto the shore. Energy is transferred or transmitted or moved from one place to another, from their point of origin to the shoreline where they crash. And you can sense that energy if you've ever gone boogie boarding or wave surfing or jumping the waves, or even just examining the chewed up bits and pieces we call sand on a seashore. Those are all originating from something larger that was broken down from the energy of the waves, eroding them over time, a topic we're familiar with from the past. But let's continue with unpacking waves. Let's begin a diagram in our book, starting with a flat line. I like to think of this flat line as a rope. In fact, maybe we'll demonstrate with a rope in the classroom, like a jump rope. So if we have a flat line, this illustrates that there is no energy traveling through this line. It's just a stationary rope, a stationary line. It's not illustrating any change or movement of energy. What if I were to take the rope and start waving it up and down, up and down? We can form the appearance of an up and a down with that rope. If I swing it, you can see it moving up and down. But it takes energy in order to do that. So we can imagine that there's some source of energy here, and it's causing this undulation or movement from one place to another. So let's diagram this illustration. The flat line itself is called rest. just a horizontal line. It's like that jump rope that's not moving at all. It's at rest. Kind of like your body position when you go to bed at night. You're like flat out on the bed. There's no energy left at the end of the day. But the green line there represents the movement of energy or a disturbance moving from one place to another. And the distance between these high points is called the wavelength. So the distance from what we're going to label as the crest, because the high point of a wave is called the crest. So the distance from crest to crest is the wavelength of a wave. And different waves have different wavelengths, and those wavelengths actually identify what kind of a wave we're talking about. Now, in the context of seawater and the waves at the shore, you can count the waves that go by in a period of time to get your sequence right so that you can go surfing on the waves. Yeah, dude, catch 5. Yeah. Ooh, I'm in the tube. Ooh, everybody's surfing USA. But these aren't the kinds of waves that we're talking about this week. We're talking about the electromagnetic waves, which have much shorter wavelengths in many regards than a water wave, but not all of them. But we need to label the parts. So we have the crest to the crest, up from the rest. Distance from crest to crest is the wavelength. The very bottom part of a wave is called the trough. And if you think of agriculture and farming, maybe you have animals, cows that eat out of a trough. A trough is like a bucket or I want to say trough, but like a three-dimensional bucket stretched out where you can put food. That's what a trough is. The crest is like the crest or the top part, like on a bird. Like if you think of a cardinal, the crest of a cardinal, it has that little peak on its head. That's the high point of a wave. Now, the distance from rest to crest is called the amplitude or the height of a wave. Now, if you ever listen to the radio, I would imagine most of you probably listen to an FM radio frequency. And the FM actually stands for frequency modulation. We'll get to that later on. But maybe older people might listen to an AM radio station. And the AM stands for amplitude modulation. And the amplitude has to do with the height of a particular wave. Now, let's specifically get into electromagnetic waves here. Here's where electromagnetic waves differ from sound waves or water waves. An electromagnetic wave is actually two waves in one. It's a wave in which an electric and magnetic field carry energy. Again, they're abbreviated EMWs. E for electric field, M for magnetic field, and W for wave. So an electromagnetic wave is two waves in one. I want you to look at this diagram here. I'm going to have you reproduce a diagram similar to this in a moment, but just look at it because I think you can visualize the electromagnetic wave pretty well. The electric field is going up and down. So this wave, the lighter colored wave, going up and down, is the electric wave. Notice the magnetic field, however. The magnetic field is the darker blue wave, and it goes out and in and out and in and out. And notice that the angle between these two waves is a 90-degree angle. We call that transverse waves. Transverse waves are waves that occur at 90-degree angles or right angles to one another. Right angle to one another. So the electric field and the magnetic field are traveling at 90 degrees to one another. And now we're going to try and illustrate that in our notes. So let's imagine that we draw a flat line. This is the rest line, but this indicates the direction of the wave. We're going to draw a little arrow on it. So we have the wave direction going from left to right. We're going to draw our electric field, electric, boogie, woogie, woogie. The electric field is going to go up and down, up and down, up and down. I'm illustrating that with my green line, but I'm labeling it the electric field. And notice I have this geometric symbol here showing a right angle from rest. Now, this is a transverse wave, so it's two waves in one. Electric is just one of them. The other one is the magnetic field. I'm illustrating it here with a different color. The magnetic field is coming out and in and out and in from the rest line. And the key part here, what I want you to try and visualize is what I was trying to show you with that initial diagram earlier, that these two waves are at right angles to one another. They're traveling at the same speed. They have the same wavelength. They have the same amplitude, but they're traveling at 90 degrees to one another. These transverse waves describe how an electromagnetic wave moves through empty space. Now, as I've mentioned before, there's not just one kind of electromagnetic wave. There's a whole variety of EMWs based on their wavelength. And so right now I want to show you the electromagnetic spectrum. The electromagnetic spectrum is the arrangement of electromagnetic waves in order of their wavelengths and frequencies. And the word frequency, what I have written here in parentheses, you should add in your notes as well. Frequencies are the number of waves in a given period of time. And typically we refer to seconds per second, and one wave per second is called one cycle or 1 hertz. We talked about hertz yesterday, if you recall. So a hertz is the number of waves per second. And if we look at the electromagnetic spectrum here, we vary from one extreme to the other. Visible light is right here, almost midway, but it varies from cosmic rays on the one side to long wave radio waves on the other side. These are very long waves, and these are very short waves. So let's fill in our diagram a little bit more in our notes. We can start with just a crude diagram drawing a wave, and notice that on the left here we have longer wavelengths, and on the right hand side we have shorter wavelengths. So as you illustrate this in your notes, try and illustrate longer wavelengths on the left and label it longer wavelength, and shorter wavelengths on the right and label it shorter wavelengths. In other words, our crests from crest to crest is more spread out on the left and more squeezed together on the right. Now, as we label this diagram, we can label just the basic components to it. Generally speaking, radio waves are the longest wavelength waves in our experience. So we're going to label the radio waves on the left-hand side, followed by infrared waves. Infrared waves are also known as heat energy. We can feel the heat. Visible light comes after that. It's what we can see. Insects, by the way, are much better at seeing the ultraviolet light. If we were butterflies, we'd actually be more sensitive to ultraviolet light than to even visible light. But ultraviolet light is next, then X rays, and finally gamma rays. There are lots more identified waves within these ranges, but these are the ones that we're going to focus on right now for our discussion this unit of astronomy, because we can use these different kinds of waves from the electromagnetic spectrum to help see, using appropriate instruments, we can see these different portions of the electromagnetic spectrum in interesting ways, and they reveal a lot about the origin of the universe and the future of the universe, as well as the present of the universe. We can examine lots of things by learning more about the electromagnetic spectrum. Now, tomorrow we're going to focus more specifically on visible light, and we'll introduce what is called spectral analysis. We'll do that tomorrow, but we're going to call it quits here for the day. And so I'm going to say for now, bye bye.